So why does this become a tunnel effect right here where it's black in the middle? So if I take this whole thing and now I'm looking at p dot y, I'm multiplying that whole color value by p dot y. The UV function is going to return values between -1 and +1 with 0 in the center. So that means when I'm looking at p dot y, I've got -1 values up here, and as I get down to the middle, I get to 0, and then I go back down to 1. So since I'm multiplying this color by p dot y, it winds up multiplying by 0 in the middle of the screen, and that's why you get that black band in the center of it.
Would you go through those again? Just
Line by line.
Just repeat what you said.
UV is a function that's built into the force, so it's not a standardized thing, but it returns a vec2, so a 2-item list that gives you the x coordinate and the y coordinate of the current pixel that's being rendered. And that value is measured between -1 and +1. So then here we're just defining a frequency, and then I'm taking the sign of this, which is just, I mean, this was just me playing around and trying different things earlier, but you can get different results by trying different things right here. I think if this is what ooh, that's kind of cool. So p dot x times a frequency value. If I want more stripes, I can just increase this frequency value to get more stripes there. Or if I wanted fewer stripes. And then time, again, is a uniform, so a value that's sent from the CPU up to the GPU once per frame of video. And then the multiplying it times p dot y right there is what gives us the kind of black band in the center. Again, because p dot y is going from -1 to +1 as it moves down the page, with a band hovering around 0 in the center of the screen.
Can I just ask?
Yeah.
This might be a really stupid question. What is it that makes it move? Is it the fact?
It's the time. So time is being increased monotonically on the CPU. It's just like a phase value they're just increasing it for every frame of video, they're increasing the value of time as it goes.
And it's doing all of the pixels at once?
Yes.
So where it starts, it's a zero-sum time or at the beginning?
Yeah, I think right when the page loads, it's 0, and then it's just increasing after that. But because it's a sign, it's always going to wind up fluctuating. Whatever values you have there, it's just fluctuating between -1 and +1 coming out the end of this. I think, yeah. And then we're just multiplying it by this to get that band again. Yeah.
So how do you change the frequency of the time?
The frequency of the time. So yeah, you could just multiply time by a value, and it'll start moving faster.
Okay.
Sorry, there might be. Yeah. Does anybody have problems with flashing? That would be good to know about now. If you're watching this online and have problems with flashing, turn back now. Or similarly, you could slow it down just by multiplying time by some value here. Questions are great. Any more questions? Okay, let's look at the next one.
Do you because it's quite, you have to really think very mathematically to really have an idea before, so you just start oh, this looks cool, and because it's someone really complex, some of the shaders.
It takes a while to get your head around this way of thinking where you're coloring an individual pixel, because that's not how any other arts programming system works, right? You say, oh, I want a shape and I want it here, but this, or I want to paint a line from this point to this point. But here you're not doing that. You're just determining the color for 1 pixel every time the program runs. And so yeah, it's definitely a really different way of having to kind of wrap your brain around it. This is very similar. So UVN returns a normalized value. So instead of having values between -1 and +1, they're going to be between 0 and 1. And then here I'm just specifying some different values. I'm looking at the current X value that gets returned from UVN, and here I'm adding the result of this sine oscillator to it. And that's what's making it kind of fluctuate on the screen like that, as opposed to being the straight lines that we saw earlier. And so my final color is just taking whatever the result of this is, and then I have some type of thickness value that determines the thickness of that line that gets presented right there. I guess one other difference that's here is I'm using the color for red, green, blue, and alpha, and that helps give it that kind of fuzzy quality to it by also fading the opacity of the color in addition to the red, green, and the blue values there. So I could change this to make it thicker.
But can you have a, like vec4 is not supposed to have 4 values?
Good question. So if you give it one value,
Just
it
repeats.
knows to repeat it throughout the entire thing. And you can also do things like this. You can say vec3, comma 1 point, and it'll use this for the first 3 numbers, and then use that for the last one. If I just did color, comma 1 point, I don't think that will work, because now it doesn't know how many it should count this for and how many it should use for that. So you have to kind of explicitly tell it that you want it to use this for 3. Good question.
Another question.
Yep.
The color is between 0 and 1, no? It's mapped? I don't forgot that.
Color, so the color is just determined based off of taking whatever this thickness value is and dividing it by p dot x. And so what happens if I get rid of the absolute value? It just, okay, so then you get this hard edge on the line, whereas taking the absolute value gives it a soft edge on both sides of it. That's the only reason why that's in there, to give it that same values on both sides of the line that appears there.
There are 2 types of shaders, no? Will we go into that?
So, sorry?
There are 2 types of shader code.
Yeah, there's even more. But no, we're only going to do fragment shaders today.
Because they're like
The vertex shaders and...
But like there is like one way of writing them, like that is different for both, because I tried like writing some shaders and exporting them to this, and then there is like another syntax.
Oh, yeah,
Like
yeah,
one
yeah.
has both have the main, but some have like some C variables you have to declare in the beginning, and then you have to change some things.
Yeah, well, this is abstracting some of that setup stuff away so that you can just focus on writing the actual functions that are involved. But yeah, a lot of times you need to define like what version of the shader language you're using at the top of the shader, so the graphics card knows what to expect. And you can define extensions to the shader language that you want the graphics card to use as well, and those are all take the form of C defines.
And can you export from here? Like if I wanted to have like the final shader file.
I don't know.
Can I reuse it? That's
Yeah, I don't know. I'd have to look and see if I could figure out where to grab that from. There's probably a way to do it. I don't know what it is. There should be some way somewhere to see what the final shader code is. I don't know what it is. I can definitely show you that in my system and some of the other ones, but yeah, I don't know what it is here.
Yeah, I managed to export it from Hydra, and also like there's this shader toy, and it explains there.
Yeah,
Change the things,
do
and
it.
the other one, like there are a couple of things like.
So the next example, and this is the last one. Oh no, we'll do one slight other thing. We'll add in the FFT, but this one is, so now we're getting pretty close to like the types of things that we were seeing inside that Hexler video. And this is really almost identical to what we saw earlier, except that I have a for loop that I'm wrapping the modification to our X value in, and the modification to this color. So with color, I'm also, instead of setting it, assigning a value each time, I'm just increasing it by the current iteration of the for loop right there. And I mean, yeah, this is something I just came upon by looking at that Hexler video and kind of copying it, and it's not something I could necessarily, I mean, I can logic my way through it, but it's painful.
But why did you use UV this time instead of UV that you just used earlier?
I don't know. What happens? Yeah, it looks better. that's the answer.
And I guess we're gonna have some mouse interaction at some point.
Yeah, so you can do mouse in here. I think it's just mouse.x.
Brilliant.
Or mouse.y, whatever you want to call it. There's a whole bunch of, like I said, there's all those uniforms that you can look up the values of inside of there. And so the next thing, the last thing I wanted to do with the shaders is just add in the FFT information so that we can get these things kind of bouncing around to our microphone input or some type of audio or something else. And so I actually noticed earlier today that the audio stuff seems to be broken in Chrome, so I'm going to switch over to Firefox to do the audio part of this. So I'll copy and paste this. Let's go to Firefox. And then to get the audio to work, you just go down here to the bottom and there's a little microphone button right here. And so if I click on that, I'll tell it I want to start the microphone line in. Again, I just went to the bottom, click on the microphone button, that brings up this screen. Click on microphone line in. It asks me what I want to use. I'll go ahead and say I want to use the microphone.
It says mine doesn't support
Oh, I don't know about that.
Chrome.
It doesn't, not in Chrome. Chrome is broken with this for some reason. You use Firefox if you want.
You're in front.
Yeah. And so at the bottom here, you can see there's a little FFT readout that's showing me four different bands of data that are grabbed out of there. And I think the keyword is actually bands to get access to this. So if I go to uniform, and then yeah, I have bands that I can use to access each one of these. So let's see, if I take this and do, so here I have gain equals 1. If instead of doing that, I say bands 0. Now there's something that's happening with the audio.
What? Also.
And we could feed music into this instead. There's different hacks for feeding the music into it. There's the hack of taking the music out of your computer and routing it back into the input, or running it from your phone into the computer. There's the hack of just playing it on your computer and using the computer's microphone to then pick up whatever it is that you're listening to it. There was some open source package that just got released. I don't know if anybody knows the name of it off the top of their head for Mac, that lets you do this. I just saw an article about it not very long ago. I bought some software called Loopback a long time ago that lets me route all the audio on my computer.
It's called Black Hole.
Black Hole,
Yeah,
yeah. So if you're on OS, is that OS X only or is it all?
I don't know.
I think it might be cross-platform. So if you need software to kind of route audio into your browser, Black Hole, it seems like it might be a cool option to be able to do that. Lots of different ways to get the audio in there. Yeah.
So this bands is kind of an array or?
Yeah, so it's 4 values, basically he has it divided into low, mid, high, mid, and then high. And we'll look at the code to see how that works in a second.
Okay, cool. It's so easy to get something cool out of it, like just experimenting with the parameters. And
Yeah, I mean, I think it's hard to understand what you're
Yeah.
doing, but it's easy to just start like tweaking things and seeing what happens, and then so that's just p.x, but p.y, now I get this like weird looking crossy-ish thing, or multiplying it gives you that type of weird effect. What else can we do? We could take the power of x raised to the power of y. Now we get this thing that's happening on there. Or the log, or wait, tangent. Ooh, tangent's nice. Wait, that's an error. That's still the power. Atam, that's what I meant to do. And then the power of that raised to... That didn't work.
why is the quality so bad sometimes?
The quality of...
Like I made this very trippy thing here, but the quality is super bad.
Yeah, so you're getting like a feedbacky thing inside of there. I don't know what the resolution is set to. He might be clamping the resolution. And so one problem that you'll have with shaders, if you're running it on like a retina display, is basically you have 4 times as many pixels all of a sudden that you have to render. And it costs a lot more on the graphics card when you do that.
So if you have a better video card,
Yes, it'll run faster, but he might be limiting the number of pixels that he renders it to explicitly inside of his software. I'm not sure.
okay.
Okay, let's look at really quick. Let's look at the Fft code, and then I think there's a coffee break scheduled. So I have in the gist, I have a link to the actual part of the code where he does the Fft. I don't know if everybody in here has done FFTs with web audio before. I put another link inside of there to a tutorial that I made a while back that goes through step by step how to do an FFT using the web audio API and show the results using the HTML canvas object. So if you've never done it before, there's a reference in there to learn how to do it. But really what I just wanted to focus on inside of here was how he splits the audio into these 4 different bands. So he's running an FFT of 1024, that's the window size for the FFT. So every 1024 samples, the FFT runs its algorithm. And the way the FFT works, you basically get half the number of bins compared to the size of your window that you have. So you get 512 bins of frequency data when you run an FFT with a window size of 1,024 samples. The Y doesn't really matter, but just know that you get half the number of bins back. And so then this little chunk of code right here is basically going through and dividing up those bands. So the low part of the FFT, the band 0 in the force, is basically giving you bins 0 through 5. The low mids is going to be 5 through 11. The high mids is going to be 11 through 24. And the high frequency bins are going to be 24 through 512. And this is because pitch is perceived logarithmically, but the FFT bins are all spaced linearly apart from each other. So you have much fewer bins in the low frequencies than you do in the high frequencies, at least perceptually, in that way.
So bands can only have 4 values maximum?
Well, so we have 512 maximum values, and he is making it easy for us by saying, I'm just going to make it low mids, high mids, and highs, because having access to bin number 337 doesn't really mean anything. And so what he's doing is going through and summing these bins to get each one of these different values. So this is the for loop that's going through and summing the first 5 bins and storing that in the low value, and then it's going down. And the math, I don't know if I could explain all the precise math that's happening here, but he's just looping through the different bins and storing it in the lows, the mids, upper and high.
You're mapping each one of the frequencies that you have to like a specific parameter in a shader? Or?
You're mapping the sum of all the bins of the FF. Okay.
Because you're separating you're doing a Fourier transform to separate the audio information.
So yeah, it's giving you 512 pieces of information per sample, basically, per window of samples. And so the idea is, instead of saying, I want to map bin number 300 and whatever to this parameter, you're creating 4 different bands of bins. So I can say, I want to map the high frequencies to this parameter, and I want to map the low frequencies to this parameter.
Okay, so this is not, once you put bands, you're not you need to map them to something.
Yes.
Yourself.
Exactly.
Okay.
Yeah, so that's what I did up here.
The gain.
So gain equals bands 2, or bands 0, or bands 1, whatever else. I don't think I did it. Probably the way I've got the code set up right now is probably not going to look that different depending on what band I'm using. But
bands 1, what it's doing is actually just taking that kind of one that was in the high and in the middle range.
The low mids.
And the rest is not being actually mapped to the gain.
Yes.
Okay, that was my question.
Yeah.
Yeah, what's happening there with the array? Okay. Interesting.
I think we were actually supposed to go for a little bit longer before we do the break. Let me just show a video of Sean performing with this tool. And then when we come back, we'll kind of throw away the shaders for now, kind of with, hopefully we have some understanding of how they work and what the graphics card is doing. And then we'll look at some higher level systems that will compile shaders for us based on some higher level descriptions.
Maybe a last question before you move on to the video. So you don't actually have access to the frequency values, it's just this low, mid,
That's all,
abstraction kind of thing.
Yep. So the FFT is giving you 512 readings that are covering the entire frequency spectrum, and then Sean is saying, let's just sum those into 4 different bands. Low band.
Because that's what you need to make something with it.
It's just aesthetically, it's really hard to think about dealing with 512 parameters and
Right.
many of them will be useless depending on what's happening. Some of them will just fluctuate so widely that they'll basically be noise. So he's kind of just averaging them into 4 different bands to try and make it more useful for people.
Very cool.
And when was this? How old is this?
8 years, 7 years, 7 or
Okay,
8
this
years.
is already one of the other ones.
Yeah, it's been around for a while.
And is this like the bands thing? Because that I'm sure like the other ones are also good, but I haven't really gone into like how you actually connect the audio to the.
How to connect the audio in this one?
Like in general, is this like a kind of general approach?
It's the normal web audio, way to like read in the microphone and to do that.
I think what makes it difficult to understand is that it does a lot of magic for you
Yeah,
under the hood. So like you're explaining about the frequencies like low mid, but you kind of have to understand how FFT works.
FFT works.
from audio
Yeah,
sound.
maybe I'm assuming too much.
But yeah, maybe like
Let
showing.
me think about that. Maybe when we come back from the break, I can do a better explanation of how the FFT is operating in this
I think it's kind of
context.
boring to see like the array of frequencies
Yeah.
and kind of like it changing, but maybe it would be useful to
Yeah,
understand how
maybe.
it goes from signal to.
Let's look at a video of him first, though, and then.
If you put like if you don't put time and you put like 0.1, you can actually pause the thing. It's cool.
Nice.
Like
Yeah,
you can
that
have
makes
like
sense.
some control about like how like it's like a fixed kind of image looks. That's very nice.
job is like
But
ridiculous.
it's really
What
cool.
the heck?
Very into it. We just have to turn off the light.
I'm turning it to the left and it's just bright red now. It's broken.
Maybe on the computer. if you just lower
Yeah, can I turn it
here.
down and Vimeo? Yes, I can. We know why that works now. He's just multiplying times p dot y somewhere. And now he's got a black band in the middle.
What's that S noise?
Simplex noise, it's just a classic type of noise that is not like pure white noise. It has like some definable characteristics, so you can, when you modulate it over time, you can see it kind of moving in identifiable ways.
Like in the molecule? Is this video available on?
It's in the gist, yeah.
It's really cool.
Cool. Okay, let's have some coffee and then we'll come back and we'll do some Hydra.